In this second question, we have some organic chemistry. We have chloroalkane, so this is halogenoalkane, and we have acyl chloride, which is RCOCl. They each react with water, and there is a reaction you will call hydrolysis, but only acyl chloride fume in the moist air because acyl chloride is very reactive to hydrolysis, very sensitive to hydrolysis. The acyl chloride fume there, the fume is actually HCl gas. So which product caused the fumes? It is not hydrochloric acid, it's the hydrogen chloride. Hydrochloric acid will still be in solution. So if you write hydrochloric acid, you got to think about what hydrochloric acid actually is. HCl aqueous is not a gas. Acid is dissolved in water to give you H+, so that cannot be the answer there, because it is not a gas, it's not the fume there. Explain why the reactivity of chloroalkanes and acyl chloride differ. For that 1 mark, we're going to think about the system here. So RCOCl, 2 highly electronegative atoms, oxygen and fluorine, versus halogenoalkane, so just RCl like that, delta negative, delta positive on the carbon. So what we can say is 2 highly electronegative atoms. So chlorine is not like in the top 3 of electronegativity, but you know, it's still halogen, it's still very electronegative. So 2 highly electronegative atoms, chlorine and also oxygen. Well, since I already started using symbol, I might as well use symbol. 2 highly electronegative atoms withdraws electron density from carbon in the acyl chloride. So your carbon become more susceptible. So that carbon becomes very delta plus, that means electron deficient, and therefore it would be very easily and susceptible to attack from the water, which can act as a nucleophile as you have lone pair on the water. Part B, so we have compound R. Compound R is this thing here, and is a useful intermediate in the synthesis of blah blah blah. You can make R from compound P. Compound P is a hydrocarbon, compound containing carbon and hydrogen atoms only, and from there you can get this carboxylic acid. We think about carboxylic acid bonded to a benzene ring as benzoic acid, and this is also benzoic acid. So this is a dibenzoic acid, something like that. So we can think about benzene chemistry. Which one will allow you to give you benzoic acid? It has to be the oxidation of alkyl side chain, and this is only possible when you do it in acidified KMnO4, and you have to reflux this. Okay, so very strong oxidizing agent there that can oxidize any alkyl long chain on the benzene, and they will convert this to carboxylic acid and this to carboxylic acid. 6 carbon inside there, 7 and 8 carbons. So 4 hydrogen there, 1, 2, 3, and 4. 2 of them got substituted. Carbon from 4 bond, you only show 1, so there is a 3 hydrogen and 3 hydrogen, 6 hydrogen, 7, 8, 9, and 10. So you know, this will give you that. That started with skeletal formula. I'm just going to maintain with skeletal formula. I'm sure if you write CH3 and CH3, they will have been alright as well. Step 2, so step 1 just now was oxidation, was the type of reaction. Step 2, we're going to substitute the OH and become Cl. So these are acyl chloride, which are much more reactive compared to carboxylic acid to nucleophile. So this type of reaction, the type of reaction is going to be what you call substitution, because you are exchanging or replacing the OH with Cl, and typically you need something like S or Cl2, or you can use PCl5 to achieve this thing to make acyl chloride in A2 chemistry. In step 3, this amine, this is 2 carbon amine, this is called ethyl amine, and they have lone pair on the nitrogen, this is the nucleophile, and then you have got delta plus on the carbonyl carbon of acyl chloride, very susceptible to attack on these by this nitrogen lone pair. So this is going to do a condensation reaction. It's a condensation reaction because you are going to form an amide. When you form amide, that reaction is called condensation. When you form ester, that reaction is called condensation. This is in AS Introductory Organic Chemistry syllabus, and you will see that the product is going to be O and then NH and then like that, CH2CH3. But my concern is, if you see this properly, you will see that there's only one nitrogen, and that is because after you do the first condensation on here and you kick out HCl, you are going to do a second condensation as you still have a lone pair there, and that lone pair can attack on this delta plus carbon, and it's going to do a condensation reaction where it does nucleophilic addition onto the carbon-oxygen double bond and then elimination of the Cl minus. Overall, what you're going to get will be without that thing there. So what you're going to get is the nitrogen is going to come together and they're going to link them together like that, and you will get the CH2CH3 here. That is why you only have one nitrogen there, because you do double condensation reactions, and this reaction will give out 2 HCl. As you do one condensation, give out 1 HCl. The second condensation loses the other H and the Cl as this steamy white fume. 6 carbons, 7, 8, 9 and 10. So 1, 2, 3 and 4 hydrogen, no hydrogen there. 5, 6, 7, 8, 9 hydrogen in this molecule, to 1 nitrogen and 2 oxygen. And from there you can get here, when you reduce amide, this is amide, this is not ketone because next to it is carbon, but next to it is nitrogen, CONH. In this case you don't have an NH because it's already been used to form these cyclic amide here. So this is an amide, this is also an amide. This is called reduction. The type of reduction is reduction of the amide group. And to reduce amide is in the A2 syllabus under amine and amide chemistry. You need things like LiAlH4, lithium aluminium hydride. You do this in dry ether and you reflux that. Okay. Suggesting the structures for the starting material P and the intermediate Q, I already gotten the 2 marks there. Suggesting reagents and conditions for the following steps for the last 3 marks. Step 1 was your oxidation of alkyl side chain there. So I have decided to use the acidified KMnO4. And also the conditions, because as stated in the question, reagents and conditions, do not forget that. The very next thing was step 2. We're trying to convert this carboxylic acid to acyl chloride. So this was the substitution reaction, and we can use things like PCl5 or SOCl2, or you can use PCl3 as well. The last one, step 4. Step 4 was this one, not step 3. Step 3 was substitution. They already provided you the reactants, and this was usually done with this in ethanol. This thing in ethanol is the solvent, and then reflux to make sure it happened. The very last step was reduction of amide. You need the lithium aluminium hydride, and this is in dry ether. I think, if I'm not mistaken, sodium borohydride can be used because it's not strong enough to reduce amide. Just like sodium borohydride is not strong enough to reduce carboxylic acid to alcohol, it wouldn't be strong enough to reduce the amide to amine, if I'm not mistaken. But we'll just stick with this because this is as stated in the syllabus. The reduction of amide, the reduction of nitriles to amines, both of them can use lithium aluminium hydride there. Okay, there's also another choice, if I'm not mistaken. You can use hydrogen and nickel catalyst, hydrogen molecule and platinum catalyst, and heat. That should also work to reduce the ketone there, to reduce the amide as well. Okay, in terms of this PCl5 SOCl2, so you should be able to write an equation. This is just a general carboxylic acid that you can write with PCl5, and that should give you RCOCl. Plus POCl3 plus HCl. That will be your steamy white fumes. As this reaction progresses, you have got 2 carboxylic acid, so there and there. So when you have 2 carboxylic acid, you can imagine you have 2 of that and 2 of that, and you get a diol chloride because you get 2 times acyl chloride, and you get 2 of that and 2 HCl. How about when you use SOCl2? Similar kind of chemistry, so that thing plus 1 SOCl2, you're going to get the acyl chloride as the OH get replaced with chlorine and you get SL chloride. Now the SO combined with the oxygen, you get SO2. And last but not least, you can also get the HCl steamy white film as your observations for this reaction. When you convert the OH of carboxylic acid into SL chloride, both of these are done at room temperature. It's a very exothermic reaction. If you heat up any further, it might be dangerous in the lab. And that's the end of that 7-mark organic question there.